out cross validation, and the last one is the bootstrap method. So we will understand these 4 types of cross validation one after the other. Let's start with what is holdout method. This is probably the most famous one, the famous cross validation method. You might have already used it if you have gone through some of my videos in on different case studies. I have mostly used the holdout method while demonstrating the cross validations. So what you essentially do in holdout method cross validation is that you divide or you split the data, the sample data, into 2 types or 2 subsamples. The first subsample, you call it as a training sample. You use that sample to build a model, and you have another subsample which is not part of the training sample, and you call that as a holdout sample, and you test your model. In the holdout sample. We also call that as testing sample. If the model statistics are consistent across these 2 samples, we are confident about the fact that the model is going to perform well in the new data. It's not just the training data on which the model is performing well, it's also going to do well in the new data. So normally we go ahead with 50 to 70% of the data in the training sample, and 30 to 50% as the holdout sample. Although these numbers are not there is no thumb rule as such, but yeah, normally the industry practice is to take 50 to 70 or 80% as training sample and 20 to 50% as the holdout sample. So if you're building a regression model, just check out the mean square error, the root mean square error for training sample, and also check that out for the holdout sample, and if they are very similar to each other, then the model is not an overfit. Otherwise you have to go back and rebuild a model, ensure that the model is the sample that you are using is representative, and so on. One bad thing or one disadvantage of using holdout method is that it is prone to sample bias, because you do not actually decide which observations are going to be in the training sample and which observations are going to be in the holdout sample. You do it randomly. You just do a random sampling. You do a random sampling in finding out which sample is going to be in the training sample and which data point is going to be the training sample and which data point is going to be in the holdout sample. And that's not a very representative, so to say, because if you change the splitting pattern, you probably will get a different result. The chances are low though, but there is definitely a chance that you will get a different result. For instance, you just took this sample, okay, this one as the training, and this portion as the sample in the extreme left, this 30% of the sample as the validation sample. You probably get a different result than what you had got in the previous one. So this is prone to sample bias. So the next one is the KFold cross validation. KFold cross validation is the type of cross validation in which you split the sample into k equal sizes or k equal subsamples. Let's say, and the k can take any number. Okay, it can take 1, 2, 5, 10, any number. In a sample, let's say there are n observation, and you have taken k subsamples. So the number of samples or number of data points in each sample would be n by k, n upon k. Okay, so each subsample should have the equal number of observation or equal number of data points. Say for instance k equal to 5. So what you do is that you divide the entire sample and into 5 subsamples, each having n by 5 n upon 5 data points. Okay, and you just take one of the subsample as the validation set and the rest of the 4 take as the training set, like the way we have done here. This is a training subsample, training subsample, training subsample, but the 4th one is a validation one, and then you take the 5th one as a training sample. So we build a model by using the data for the training samples and use the validation sample to validate it. Okay, so how do we validate it? The way we did in the in the previous slide. We'll use the same root mean square root mean square error. If it is a regression problem, if it is a classification problem, you can actually use accuracy rate to see if it is consistent across validation and training sample. Now that's for one iteration. You have to do it for 5 iterations because the the validation sample can be any one of these 5 samples. So this is the 4th one, the 4th subsample is the validation here. You can actually take the 5th subsample as the validation as well. Just change it. Okay, this has become validation and this is training. Okay, so now you build a model by including training samples 1, 2, 3 and 4th one, and then you validate on this particular one, the last sample. Okay, and you keep on changing that, right? So there will be 5 iteration. Validation sample could be this one, this one, this one, or this one, and this one. And every time you will get an error rate, right? When you validate your model, you will get some sort of a error, right? It could be any of these error, pure modulus of the error, or you're simply squaring it and taking the square root. You are actually using the root mean square error rate. So you will get some sort of an error while doing the validation for each of the samples. So the prediction error would be just the average of the error you are getting for each validation set. So if I have k validations, you will get k errors, and you just divide that by k, you will get the average error, which is your prediction error. Okay, so that's called KFold cross validation. Normally people take the k to be 5 to 10 because otherwise it takes a lot of computational time to do all these iterations, right? So here it's 5 subsamples, so we have just 5 iterations. If it is more, it would take a lot more time. The advantage of this particular method of cross validation is that it doesn't matter how the data gets divided. Remember, in the holdout sample model cross validation, we had the problem of how we split the sample. If you change the splitting pattern, you probably get a different result or different prediction error. But in KFold cross validation, it doesn't matter much. So that selection bias will not be there. Selection bias will not be present. Why is it so? So let's go back and understand why is it so. Now remember, in holdout sample cross validation, so the validation set that you are taking is completely different from the training set, right? It's completely different. The data points in the validation set will never be present in the training set. So that's the that's the criteria for holdout cross validation. Whereas here in this case, the validation set is, or the validation subsample is actually changing. So every sample, every data point would be part of training sample and part of validation sample, right? Because validation set can be this one, can be this particular one, can be this split as well, can be this split, can be this split. Similarly, a training set can also be, all the splits. So every data point present in the sample will be a part of training data and will also be part of the validation data. Hence, this particular way of cross validating is free from sample bias or selection bias. The next one is the leave one out cross validation. It is it's a special case of the KFold cross validation when k equal to n. So n is nothing but the number of data points in your sample. So when the total number of splits that you are going to have is exactly equal to the number of data points in your sample, we call that as leave one out cross validation technique. So we'll do pretty much same as what we have done in the k-fold cross validation, except the fact that here in this case we do not have a subsample, so to say, as a validation sample. We just have one data point. Okay, so we just take in the one data point as the validation sample and build a model in rest of the data points, okay, and test it with the holdout data point and get the error. So you will get error 1. Now you change the data point. Okay, you just take this one. Okay, you will get the error 2. So what you will do is that when you take this one, you will build the model on the entire data point including the last one and test your model on this particular data point. Okay, and you will get an error. We call that as error 2. And for here, so we continue to do the same thing. Okay, so we'll get error 3. So you will get as many error as the number of data points. So you will get error 1 to error n if you have n number of observations. So the average error would be just the sum of the error n equal to 1 to n divided by n. Sorry, let's set I equal to 1n. Okay, so the average of the error is the prediction error for future. So just remember one thing is that is exactly the same as the k-fold cross validation, except the fact that the k in this case is just the same as the number of data points in your sample, right? So what is the problem in this case? The problem in this case is that it will take a lot of time to compute. If you have let's say 1000 data points, you will have 1000 iterations to perform. So you will build 1000 models. Okay, so you take 999 data points, build a model, test your data point on the one of the validation data point that you have kept outside, and keep on changing. Just include this here and then take one data point, another data point from the sample as the validation one, and keep the iteration going 1000 times. It's going to take a lot of time if you have just too many observations in place. In real time scenario, you will probably have a million observations to perform your cross validations, and that's going to take a lot of time. So it's a good way to validate, because you are taking every single data point out from your training data and testing how it's going to predict each observations, which is a very good way to validate, cross validate rather, but the computation time would be just huge. But the good thing is that given the fact that nowadays you have high computation power, a lot of computational resources are available by the cloud service providers, you can actually use this particular technique, and it's actually becoming a popular technique nowadays because the computational power of systems have gone up drastically over last few decades. The last one, or the fourth one, is the bootstrap method. In bootstrap method, you perform certain steps. So firstly, you randomly draw data sets from the training sample. So you have a training sample, you just randomly draw data points, and each bootstrap sample, or the sample that you have created by randomly picking data points from the sample, will have the same size as your main sample. Let's, for instance, we have a sample, we have got n observation. So what I'll do is that I'll create a bootstrap sample. I call that as B1. So I'll take a data point from here data point 1 and then data point 2. But remember one thing is that you can actually you select this data points with replacement. That means you have already taken data point D1. Second time when you actually select another data point, D1 could be the one again you would be selecting. That means it's selection with replacement. Okay, so the data points can be selected more than one time. Okay, so the number of data points in Bootstrap sample B1 will also have n data points. Similarly, you can have Bootstrap sample B2, which will again have n number of data points, Bootstrap numbers B3 with n data points, and so on. And let's, for instance, you have 100 such Bootstrap sample. So what you again do is that you refit your model. So whatever model that you have built on your training data or the original data, you fit the same model in all this Bootstrap sample data, and then you examine the model, and you examine the performance of the model, you examine the model statistics, and see whether they are consistent across Bootstrap sample or not. If they are consistent, then you have been able to cross-validate your model in a good way. So the pictorial view would be like this: is this training sample, and you selected data points with replacements, and you came up with Bootstrap samples. You will have n number of Bootstrap samples, and then you refit the model in all the Bootstrap samples and check for consistency. That's what I explained in the previous slide also. So yeah, it's just a representation. Thank you so much. Please subscribe to my channel, and you can also visit our website. Thank you.